discussing the steady diffusion equation. We have done it in 1D. Now we would want to move over to 2D. So we want to discuss the finite volume method for two-dimensional steady diffusion. So in 2D, we assume the following. We assume that the control volume omega has constant cross-section. In the z direction. So that means the following. We have our coordinate system now in this way x, y, so that we have that directly in the plane of the blackboard, and then we let the z direction go out of the plane of the blackboard, and then we shall essentially entirely concentrate on rectangular cross-sections, where we have then in the z direction, this is unchanged. So that is the assumption that we are doing there. So that will be our control volume, and we call that omega p. That is our notation with the letters again. And then we have the eastern, the western faces, the northern, and the southern faces that is below here, and they are denoted by small case letters. So that is our control volume, and we assume also that the flow variables or the thermal variables that we consider, I call them here flow variables, but it can also be temperature, whatever you like. Just we have one here for the moment, the flow variable phi only depends on x and y. And that means that we have the dependence of phi only on x and y. The time dependence was already gone by considering steady problems, and now we assume that we have no dependence on the z direction. So then we assume, moreover, that there is no diffusion over the ends. Over the ends with constant z. So that is one, we see one end here, and the other end is here in the back. Just to complete that. So the one in the back, so we have no diffusion over the front and the back. And we assume that it's just for convenience that these ends are just one unit part. So the ends with constant z are, if we are in SI units, it would be done in 1 meter apart. So that means this length here from the front to the back, we assume just to be 1 meter. But that is not important. So, now we want to look at the equation governing steady diffusion, and then we start off from the general form, and that is what we discussed in the beginning. So it is the equation that we have here. Let's see. So this equation here, and that was for control volume, general control volume omega p. And now we want to apply that to our special control volume that has then the property that it has constant cross-section in the z direction, and we shall now focus on rectangular control volumes. So that means the equation 3, that is essentially what we see here, the integral form. So equation 3 becomes for rectangular control volume following, and that is now I think 31. We have 0 because we have no time dependence here, we have no velocity, the velocity is 0. And then we have the integral over the boundary of the control volume, and if we want to be precise, we'll have only to consider the eastern, western, northern and southern, because for the front and the back we made this assumption. So there is no contribution of diffusive fluxes over the ends. So therefore we can here indicate that by considering here east, eastern, western, northern and southern faces. And there we have the diffusion coefficient gamma times the gradient of our unknown phi, and we take the dot product with the outer unit normal vector n. That is a surface integral, and then we might also have a source term where we do a volume integral over the control volume omega p with the source term s phi. So that is then the governing equation. And here we have used that we do not need to consider the diffusive flux over the front and the back, because we assume that there is no diffusion over those ends. Now we want to look at the different contributions about each over the diffusive fluxes over each of the faces. So let us start with the omega e. So that is the integral over the boundary of the control volume, and we look now at the eastern face. So that is the face that we have here. That is the eastern face here. So this one here. And what do we have to compute? Well, if we have it here, we just write it again. That is just the diffusion coefficient times the gradient of phi, the dot product with the outer unit normal vector n, and it is the surface integral. And now we have to just to think a little bit, what is the normal vector at the eastern face? Let us look now from the front. So we have now our control volume omega p, seen from, say, from looking now in the z direction, the negative z direction. Then this is the eastern face here. And the normal vector here, the normal vector at the eastern face, what is that? It is pointing in the x direction. It's unit, so that means we have 1 in the x direction and 0 in the y and the z direction. What is the gradient of phi? The gradient of phi is d phi dx, d phi dy, and here we would have d phi dz. What is that? we can see it in two ways. We can say that, you see directly here, phi does not depend on z, so d phi dz is 0. We can also say we have no variation in the z direction, so therefore we have a 0 here. So now we take the dot product of gamma times the gradient and the outer unit normal vector n. So what is surviving? It's only surviving plus d phi dx. That is only the one that is left. So that means this, in our case, for the control volume, the rectangular control volume that we consider, we have only gamma d phi dx is there, and we have the surface integral dA. And now we use the midpoint rule. We say this is equal to some average of this quantity times the area of the face E. So that means we can write that here as gamma times d phi dx at the eastern face times the area of the face E. And what is the area of the face E? Well, in our case, we shall assume that we are in the discretization process, so that means that the, let's see, if we do that again here, so that is now our control volume omega p, and we assume then that the length in the x direction of the face is delta x, and the length in the y direction is delta y. So if we assume that, then we have that the area at the eastern face, that is then this one here, that is then equal to delta y. And now in the z direction, we have assumed that this length is 1 meter. So therefore we can essentially forget about that. So then we can, what we need to do later on is then to find an approximation for this average of the diffusion coefficient under the x derivative of phi at the eastern face. And we shall do that in the finite volume method based on averages that we have in the cell P and its eastern neighbor in that case. We do it just the same as in 1D, as you shall see. So that is the eastern face, and we call this formula here 32A. And we shall do now the same thing for the outer faces. So that is then 34B, sorry, 32B. And there we have to consider the integral now over the western face of the control volume. And again, we have the diffusion coefficient, gradient of phi in a product with the outer unit normal vector n, and we have the surface integral. Now, where are we here? Well, let's see. Here we are now at this face here. So this is omega p, this is w. What is the outer unit normal vector n? It is now pointing in the negative x direction. So that means n is now minus 1, 0, 0. The gradient is still the same. So we only get from this operation here, we only get minus d phi dx. That's it. So that means this here is equal to the integral over the western face, gamma d phi d minus d phi dx. And that is a surface integral. And then we do the same thing. We say, okay, we want to approximate, or we want to represent that, actually, by the average of this times the area. So then we get here minus, and that will then be the gamma d phi dx at the western face times the area at the western face. And the area of the western face, if you look at the control volume here, that will be this delta y times 1 meter in the z direction. So that means, in that case, the area in here, the area at the western face, is simply the same as at the eastern face. Okay, so now we have the diffusive fluxes over the eastern, the western face. Now we look at the northern face. That is 32c. There we consider the integral over the northern face, and again diffusion coefficient, gradient of phi, inner product with the outer unit normal vector n, surface integral. And what is that? Well, we look then at that one. So let's see. So we have, if we have our control volume again, now we are considering the normal, the northern face. So then we have our normal vector at the northern face. What has that for, what are the coordinates of that? It's pointing in the y direction. So that means we have only a component 1 in the y direction. The x and the z components are 0. So that means when we take the inner product with a gradient, only the d phi dy survives. So that means this is the integral over the boundary, the northern face, and we have gamma d phi dy, surface integral. And then we do the same thing. We want to represent that as an average of the face. In that case, at the northern face, d phi dy at the northern face times the area at the northern face. And what is the area at the northern face? That is, we said that this length is delta x, and in the z direction 1 meter, so it's delta x times 1 meter. Okay, so then we have the representation of the diffusive flux of the northern face, and now we want to do it the same way for the southern face. And that is then the integral over the southern face d omega s of diffusion coefficient gamma, gradient of phi, inner product, outer unit normal vector n, surface integral is equal to. And now we have then we are at the southern face, and there the outer unit normal vector goes in the negative y direction, so that the normal vector here has only the component -1 in the y direction, non-zero. The others are non-zero. So that means the inner product then gets a minus d phi dy between gradient and phi of phi and n. So we get the surface integral over the southern face of gamma, and it is the minus, I write it here, d phi dy, surface integral. And then we represent that as, say, the mean, and that is then the minus, and that is gamma d phi dy at the southern face times, I need to take that away here, times the area at the southern face. And the area at the southern face, that is, again, delta x times 1 meter. So that means here the area AS is simply the same as the area at the northern face. So then we have a representation of all the 4 diffusive fluxes over the faces of our control volume. So now we can then put that together and use that in the equation 31, where we also have the source term. So then so that means then steady diffusion equation 3 in 2D for rectangular control volume omega p. Well, rectangular cross-section it's meant there. For rectangular control of omega p becomes then the following. That is then the 33. That we have still 0 on the left-hand side. So, and then the different contributions are then, now we write the area into the expression. The diffusive flux over the eastern phase is then this here. Now we write the A in here. So we have then the d phi dx times A at the eastern phase. At the western phase we have this contribution here. That is minus gamma d phi dx times the area at the western phase. And we have the diffusive flux over the northern phase, which is d phi dy times the area at the northern phase minus the diffusive flux d phi dy times the area at the southern phase. And then we have the source term. And the source term is then the average source term S bar times the volume of the control volume. So, and then we do the same approximation for the source term as we did also in 1D. So let me just give the explanation here. So where we have introduced these averages here, so they are assumed at the moment to be exact. For example, that is supposed to be the integral as we saw before. I just took it away. Gamma phi dx dA and so on. For the other phases it's essentially 32 that we are using here. So that is then, in this case, the diffusive flux over the phase d omega p, and so on. So we have then the diffusive flux over eastern, western, northern, southern phases, and the S bar, the average source, that is 1 divided by the volume of the control volume omega p. We have the integral, and we integrate the source term S phi. So that is the average source that we have here. So we have this, that is, we have the expression that we have also in the equation, and that is divided by dp, then we have the average source. If we again multiply by that, then S bar times dp is then actually the term that we have in the equation, representing the source. dp is the volume of the cell. In our case, it is then the x, delta x for the cell p, the length of the cell p in x direction, times the length of the cell in the y direction times 1 meter. So that is the volume of the control volume omega p. So then we have all the contributions. Let's see. Yes. So at this point, we still assume that this is just an average representation, or it is another representation of this integral. As I said, you can think of it that this is the midpoint rule, but in a way that this is exact. So we take this integrand at a suitable position and multiply that by the length, by the area of the face. So that is what we do here. So then we want to do the discretization now, and we do it in just the same way as we did in 1D. We first define a grid, that is, we define where we have our unknowns, where we have the faces, and then we do the discretization by the finite volume method, and that leads to a linear system, which we have to solve. So it's these three steps: grid generation, discretization, and then solution of a linear system. So, step one, that is, we call it grid generation, but it's essentially identifying where we have the grid points, where we have the faces. And that is now, in a way, a little bit different, as that's what we discussed for the two-dimensional scalar conservation laws. There we had the cell-centered method, we have now the node-centered method here. So the grid points, or nodes, are the following. They are xi, y, j. And we let the I go from 1 to ni, and the j from 1 to nj. So, and they are chosen similarly as in 1D in each direction. And let's take that. Okay, let's see how we take this here. So we have a domain, two-dimensional domain. We assume that it is a rectangular, x and y. And we assume that we have the xa is the left boundary in the x direction, and xb is the right boundary in the x direction. In the y direction, we assume that we have a yc here, and we have a yd. So that means this we call yd. And then we assume that we have an equidistant grid, both in x and y direction. They don't need to be the same. Let's see, roughly. So they should be equal. They don't need to be equal, actually. So later on we shall assume to be equal, but at this stage they don't need to be that. And I did here already a slight mistake, because I should have started by the nodes, actually. Because here we first, what I do here, that would be this for the cell-centered, but here with the grid, with a node-centered method, we first identify our grid points. So maybe we have the grid points identified here somewhere. So then we have a couple of breakpoints now here. So they have the same, in one column they have the same x location, and in the other the same y location. Just to get a few some examples here. And let's see. So now we assume that these are our grid points, and for example, if we would say this is the either the P or the ij, so then this location would be then the xi, and this location would be the yj, right? That would identify this grid point ij. Then we define now the faces halfway. Here is one, halfway is roughly here. Halfway here is about here. Here it's longer, even longer. So that is the way as we also did in 1D. We define the faces halfway between the grid points. So that was now giving us the faces then in x direction, in y direction. We do it similarly. Halfway. That is then our grid, and we can then say that the faces are chosen halfway between the nodes. So the faces are chosen halfway between the nodes. Okay, now we want to do the indexing to continue that further. So we have here the one way is by the indices, the other is by the letters P, E, and W. So if we do that first, we have the P, that is the control volume that we shall focus on. This is then the eastern node and also eastern control volume. That is the western, this is the northern, and this is the southern. And regarding the faces, they have small letters. So here it would be lowercase e, lowercase w, lowercase n, lowercase s. So they are then the faces. And the indices, if we want to do that now, it is easy. This is then the I plus 1j, this is the I minus 1j, ij plus 1, and ij minus 1. Let's see. Yeah. Regarding the ordering, we can do it the following way, that we start here by 1, 1, and that would be 2, 1, and the last one would be ni, 1. This would be 1, 2, and this would be 1, nj. And The very last one in the right corner would then be Ni, Nj. If we want to take into account the boundary conditions, we can do that. Then we would do that by taking this at the x1 location, at the boundary, and we could give that the index 1, 0. We could also take the boundary condition at the upper, at the northern face of the domain, at the northern boundary of the domain into account. Then that would be 1 nj plus 1. In the same way, let's see, we could do that in the y direction. We could take into account the boundary condition at the boundary xa. Then that would have the index 0, 1. Without the brackets. And the boundary condition at the right boundary of the domain would then get the coefficient ni plus 1, comma 1. So in this way we can then take the boundary conditions into account if we do that. And you see then we have ni interior nodes, but when we take the boundary conditions into account, then we have ni plus 2 nodes. Because we have these ni, this boundary condition, and this boundary condition. In J it's the same. We have nj interior nodes, and the boundary conditions are 2 more. Here 0, and here nj plus 1. In the code that you got, the skeleton, the npi is the number of points including the boundary points. So in our example, the npi, that is for the x direction, would be ni plus 2. And in the y direction, it would be nj plus 2. So then we have defined our nodes, and we have defined our faces. And the finite volume method that uses this set where we start from the nodes and by that define the faces halfway, that way to define the finite volume method is called node-centered finite volume method. So based on such a grid is called node-centered. Finite volume method. So then we identify by the nodes the location where we have our cell average stored. Now we want to do the discretization, and then we need to approximate the diffusion coefficients, the diffusion coefficient and the derivatives at the faces. That is then the step 2. And that is the discretization with the finite volume method. So the gamma and the phi dx for the eastern and the western face, that is at east and west, they are approximated as in 1D. Just the same. And we just need then the eastern and the eastern point, the value at east and our node P, to approximate the gamma here, either by arithmetic average of gamma. If you want to take the d phi dx, we take phi e minus phi p divided by the difference in x. So it's exactly the same. the AE is equal to the AW, and that is then equal to the Y at the northern face minus the Y at the southern face times 1 meter in the Z direction. And the gamma and the d phi dy are then approximated similarly. So the diffusion coefficient and the y derivative of phi at the northern and the southern faces are then approximated similarly. And that is, for example, at the northern face we would use 34a either for the gamma n the approximation 1/2 gamma p plus gamma n. That would be the arithmetic average, or we would use the approximation, I write it here equal, but they are actually approximations, 2 times gamma p times gamma n divided by the sum of gamma p and gamma n. You see, that is just the same as we did in the x direction, where we take these into account. Here we do it now the same way with p and n, as we did with p and e. And the derivative, d phi dn, is then approximated by the following. 25. We say that the d phi dy at the northern face is then approximated by taking the value at n minus the value at p divided by the distance, and that we can write the distance in y between p and n. And the area that we have, that is the AN is equal to the AS, and that is equal to the XE minus XW times 1 meter. So it is, that is the delta x then. This distance XE minus XW times 1 meter. That is the area, the face area. That was the face area for east and west, and this is the one. Okay, so then we have the approximations, and then after the break we shall use these approximations in this integral form of the steady diffusion equation.